Great. Classification of discrete time systems. If you remember, we said discrete signals are obtained from continuous analog signals through the process of sampling. Okay, you have an analog continuous signal, you sample it at a predetermined sampling rate, and then what you obtain is a signal that is composed of discrete values, but these values basically are equivalent to the values of the continuous signal at the sampling instances. Okay? And we said that systems that are used to manipulate discrete signals are called discrete time systems. Last time we gave a few examples of what a system can typically be. And we said that, for example, if you had an operator, okay? For example, you have a transformation T, okay? Such that within this transformation, you have an input X, which gets transformed into an output Y, okay? Then this is what we call our system. The system that transforms an input X into an output Y. We said systems can be as simple as not complicated operations. For example, you can say that your Yn, okay, is going to be equal to X n minus 1, meaning that you're going to shift the values of X by one position, okay, to the right. That means you had your input as Xn, and you have now your Y, the output as Xn minus 1. It means that you're getting Xn, if for example, this was your 0 position, and you had, for example, these inputs at 0, 1, and 2, it means that your Y will now be X, but which has been shifted by one position. So you have 0. This time, if there was a 0 before 0, then that 0 will shift by one position, and we will have your signal shifting by one position to the right, so that this now becomes your 1, 2, and 3. You have shifted this. This is a time shift. Okay. There are several applications that systems can do. This is just an example of a discrete time system which operates by causing a time shift in the input to give an output. So we want to classify discrete time systems. And we're saying that in the analysis, as well as in the design of systems, it is desirable to classify the systems according to the general properties that they satisfy. In fact, the mathematical techniques that we develop in this and in the subsequent chapters for analyzing and designing discrete time systems depends heavily on the generated characteristics of the systems that are being considered. And for this reason, it will be necessary for us to develop a number of properties, okay, that can be used to describe the general characteristics of systems. We stress the point that for a system to possess a given property, the property must hold for every possible input signal. that system. So if it is a system and you're going to give it a certain characteristic, then it means that that characteristic must stand, must hold for all inputs. So if a property holds for some input signals but not for others, then the system does not possess that property. And thus, a counterexample is sufficient to prove that a system does not possess a property. Okay, so however, to prove that the system has some property, we must prove that this property holds for every possible input. I want to try to give an example. When we say that the multiplication sign is commutative, when we say that A times B is equivalent to B times A, okay? If I say that this holds, that this operation holds for A and B, it definitely means that for any value of A, okay, and for any value of B, then this property must hold. It shouldn't hold for one value of A and not for another. If it doesn't do for that, then we would actually say that it doesn't exist. That's why we say that A, for example, the dot product, we say that A dot B is equivalent to B dot A, okay? But of course, we also know that A cross B for the cross product is not the same as B cross A, meaning that the scalar product A dot B has a property, but the vector product A cross B does not have that property, okay? Meaning that you cannot say that that property exists if it cannot be satisfied by all the inputs. Okay, let's look at some of the properties that we are talking about. Okay, we want to look at dynamic versus static systems. It means that a system can either be classified as static or it can be classified as dynamic. Okay, and we're saying that a discrete system is said to be static or memoryless. Okay, static or memoryless if its output at any instant n depends at most on the input samples at the same time, but not on past or future samples of that input. Memoryless is the same as static. Actually, most times we say we use memoryless or actually memory. Okay, however, they mean the same as static and dynamic. Okay, we're saying that it is called memoryless. Memoryless means that it doesn't remember, right? Memoryless if its output at any instant n depends on the input sample at that same time, but not on the past or future samples. So it can only produce an output for a particular time input. So it cannot calculate a cumulative sum because the cumulative sum would have to take into consideration the past inputs. For it, it only understands the input at that point. Okay. So in any other case, the system is said to be dynamic or to have memory. Okay. So if the output of a system at a time n is completely determined by the input samples in the interval between n minus n to n, okay, the system is said to have memory. It means it can actually remember inputs at instances past. Okay, it can remember inputs at past instances. Therefore, it has memory. So if n was equal to 0, the system is said to be static, meaning it has no memory. It is memoryless. So if n lies between 0 and infinity, the system is said to have finite memory because you can define the length, okay, of the samples. Whereas if n is infinity, then the system is said to have infinite memory, meaning you cannot actually count the number of memory positions. So it has infinite memory. So the system described by the following input output equation, for example, yn is equal to axn, yn is equal to nxn and plus bx cubed n. You realize that this is only appearing at position n, the same position all the time. So it means that this is memoryless. Okay, it is said to have memory when we say that it remembers instances before n or after n. Okay, n minus 1, actually we can say n minus k if you want to say that k is valid from 0 up to n. It means that your system, for example, for this, okay, if you wanted to write this as a function, you would basically be saying that yn, okay, is equal to, when you start with k equal to 0, is equal to k, rather is equal to xn, okay, plus we are moving from k equal to 0 to k equal to n, and of course n is positive, so this is going to be n minus 1 plus x n minus 1, okay, plus x n minus 2, and you continue up to where you reach x into n. Okay, oh, this was n minus k for k equal to 0 up to k equal to n. So when you have n minus n, okay, so you see that this system basically has memory because it has an input at n, but also has an input at n minus 1, it has an input at n minus 2. So it can remember all these inputs. So it has memory. While for this one here, the upper system here can only be valid at a single value of n. Okay, so we say that it doesn't have memory. The first one, while this one down here has memory. Okay, so the system is described by 2.2.9, this one here, and 10 have finite memory. Finite memory because you can count. These are two values, xn and xn minus 1. These are two, they are finite, they are countable. This is going to be n plus 1 values, so they are also countable. But this k equal to 0 to k equal to infinity, you do not know where it ends, so they are uncountable, and that's why we are calling it infinite memory. We observe that static or memory systems are described in general by inputting equations of the form y is equivalent to the transformation of xn at n, okay, at n strictly, and they do not include delay elements. That means that they are memoryless. The other classification, we have time invariant and time variant systems. Time invariant and time variant systems. Okay, so we can subdivide the general class of systems into two broad categories: time invariant systems and then time variant systems. Time variant systems and time invariant systems. Okay, we're saying that the system is called time invariant if its input output characteristics do not change with time. If its input output characteristics do not change with time, we say that the system is time invariant. Okay, To elaborate, suppose that we have a system T in a relaxed state, which, when excited by an input xn, produces an output yn. Thus, we can write that yn is the transformation of xn. Okay, now suppose that the same input signal, is delayed by k units of time to yield xn minus k, and again applied to the same system. If the characteristics of the system do not change with time, the output of the relaxed system will be yn minus k, and the output will be the same as the response to xn, except that it will be delayed by the same k units in time that the input was delayed. So this is just to define a time invariant or shift invariant system as that a relaxed system T is time invariant or shift invariant if and only if xn is acted on by the transformation or by the system T to give yn, the same system, rather the same system produces the same output, only that this time there will be a shift in time. Okay, it means that a shift in the input will appear as a shift in the output. That is time invariant. If a shift in the input, okay, if a shift in the input appears in the output, then we say that the system is time invariant. Okay, so for every input signal xn and every time shift k, the time shift when applied to the input also appears in the output of the system. Okay, we're saying that to determine if any given system is time invariant, we need to perform the test specified by the preceding definition. So we excite the system with an arbitrary input sequence xn, which produces an output denoted as yn. Next, we delay the input sequence by some amount k and compute the output. Okay, so that we can write the output as yn, y as a result of n and k. K is a shift, okay, being a transformation of x that has suffered the shift k. So if this output for all possible values of k, then the system is time invariant. If it is true for all values of k, then we say that the system is time invariant. If, on the other hand, the output is not equal to this, meaning if the shift does not appear in the output, then even for one value of k, then the system is said to be time variant. Okay, we're saying that a system is said to be time invariant if a time shift in the input appears in the output also. Okay, so we can try to prove that for a given system to know if actually a shift in the input will appear in the output for us to classify our system as time invariant or time not. Okay, so we have two system classifications so far. We have memoryless and having memory or static versus dynamic. Then we have time invariant versus time variant systems. Okay, which other classification we have? Linear versus non-linear systems. When do we say a system is linear, and when do we say it is not linear? Okay, the general class of systems can also be subdivided into linear systems and non-linear systems. So a linear system is one that satisfies the superposition principle. We need to understand what the superposition principle is. Okay. A linear system is one that satisfies the superposition principle. Simply stated, the principle of superposition requires that the response of the system to a weighted sum of signals be equal to the corresponding weighted sum of responses to the outputs of the system to each of the individual inputs. Okay, so if, for example, you have, so we are saying that in the first case, we said a system with a single input yxn would be equal to t xn. Okay, so what if we had more inputs? What if we had more inputs? Okay, and you had y as the output, given x1 as the input, x2 and x3, and maybe up to xn. Would the output actually act on each of the individual inputs, or would that fail? If it can, then we would say that it is linear. It has the principle of linearity. If it can't, then actually we would say it is not linear. For example, a system is linear if and only if the transformation on the different inputs x1 and x2, okay, is equivalent to the sum of the transformations on each of these inputs. Okay, if the transformation on each of these inputs can be independently represented, then we would say that the system is linear. Okay, for an arbitrary input sequence x1 and x2, or even actually more inputs, and the constants are also arbitrary, a1 and a2. Okay, using the pictorial here, we're saying that if you have x1 and x2, okay, with linear constants a1 and a2, and you have your system operating on them to get y, okay, it should be similar to if you had this system operating on each of the inputs to give you the output y. This is when you would say that the system is linear. So the superposition principle embodied in this relation, in this equation up here, can be separated into two parts. For example, if a2 was 0, okay, then definitely that would reduce to a1 y1, okay, and y1 would be the transformation on x1. So if a system can actually satisfy the superposition principle, then it is said to be linear. Okay, we're saying that the relationship in this equation here demonstrates the multiplicative or the scaling factor of a linear system. That is, if the response of the system to the input x1 is y1, the response to a1 x1 is simply a1 y1, because a1 is just a scalar. So thus any scaling of the input results in an identical scaling of the corresponding output. Scaling of the input results in an identical scaling of the corresponding output. Okay, so suppose that the constants a1 and a2 is equal to 1, then basically we would have the transformation on each of the inputs becoming y1 plus y2. And this relation demonstrates the additivity property of a linear system. Okay, linearity actually We are saying linearity can follow the multiplicative or the scaling property, but we're also saying that it can follow the additivity property of a linear system. The additivity and multiplicative properties constitute the superposition principle as it applies to linear system. Okay, so linearity, the linearity condition embodied in equation 2.2.6, this one here, okay, 2.2.6, can be extended arbitrarily to any weighted linear combination of signals by induction. So you can have A1, A2, A3, A4, A5, A6 up to AM. Okay, so if we take AK, where K is an integer, then you can actually take any values for this coefficient AK. Okay, so we are saying that when the system, when xn given by this is transformed by the system t to give you yn, then after it is the same as you having akyk n when k is an integer. So we observe from 2.2.7 that if a1 is 0, then yn equals 0. In other words, a relaxed linear system with 0 input produces a 0 output. Okay, a linear system with a 0 input produces a 0 output. If a system produces a non-zero output with a 0 input, the system may either be non-relaxed or it is non-linear. It's very important. Where have you ever seen that? Where a system will give a non-zero output even when it has a 0 input. Okay? And we're saying that if a relaxed system does not satisfy this proposition principle as given by the definition above, then it is called non-linear. So it is either a linear system if it satisfies this proposition principle, otherwise it is called non-linear. Okay, and we can try to prove or to determine if a system is linear or if it is non-linear, okay, by using these examples. If a system satisfies the superposition principle, then it is said to be linear. If it does not, then it is said to be non-linear. Okay. We may need to go through these examples to prove if this is actually right and how it works. So we have causal versus non-causal systems. Causal versus non-causal systems. This is the third classification, and we begin with the definition of causal discrete time systems. And we say that the system is said to be causal if the output of the system at any time n depends only on present and past inputs. If the input, rather if the output of the system at any time n depends only on present and past inputs. Okay, it's said to be causal. Okay, but does not depend on future inputs. Okay, so it can only depend on the present and past inputs, but not on future inputs. But does not depend on future inputs. In mathematical terms, the output of a causal system satisfies an equation of this form, that yn is equal to f of xn minus 1 and onwards, where f is the transformation caused by that system. If a system does not satisfy this definition, it is called non-causal. Okay, and such a system has an output that depends not only on the present and the past, but also on future inputs. Okay, such a system does not only depend on present and past, but also on future inputs. It is apparent that in real-time signal processing applications, we cannot observe future values of the signal, and hence a non-causal system is physically unrealizable, cannot be implemented. On the other hand, if the signal is recorded so that the processing is done offline, non-real time, it is possible to implement a non-causal system since all values of the signal are available at the time of processing. And this is often the case in the processing of geophysical signals and images, because these ones are already stored. Okay, when they are already stored, you can actually use the future inputs. For example, if I started to tell my story about where I was this weekend, it would be difficult for you to know where the story is going. But if I have written the story down and I'm reading for you, okay, you can actually see where I'm going in future. That's the thing about causal and non-causal. Okay. So for example, when I start reading this sentence, I can say it is apparent that in real-time signal processing applications, we cannot observe future values of the signal. Okay, while I'm saying that, you are receiving the present and past, but you can actually also read ahead and see what the future has. And that means that that would have been a non-causal setting. Okay, the next classification we have here is stable versus unstable systems. So a system can either be stable or it may not be stable. And if we choose to define stability first, we say stability is an important property that must be considered in any practical application of systems. Systems definitely need to be stable. We're saying that unstable systems usually exhibit erratic and extreme behavior and cause overflow in any practical implementation. You see that? Unstable systems usually exhibit erratic and extreme behavior and cause overflow in any practical implementation. So they are not desirable. We don't desire to have unstable systems. So here we define mathematically what we mean by a stable system, and then later we'll explore the implication of this definition for linear time invariant systems. So an arbitrary relaxed system is said to be bounded input, bounded output stable if and only if every bounded input produces a bounded output. You see, every bounded input produces a bounded output. That is when we say that the system is stable. What do we mean by bounded? We would actually want to say that it is countable or it is finite. Okay? So when the finite input produces a finite output, then we say that our system is stable. Okay? So the condition on the input sequence xn and the output sequence yn are bounded is translated mathematically to mean that there exist some finite numbers say mx and my, such that xn, the magnitude of xn is known as mx and is not infinity, and the magnitude of y is known as my and is not infinity. It is, for example, if I say that my system counts all even numbers from 0 up to 20, then you know that you're going to add 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, and you'll get the sum. That one is bounded. You know the magnitude of that, okay? However, if I say that my system is going to count all prime numbers from 0 to infinity, you can never know where it will end. So it is actually not bounded. And a system that does that would be said to be unstable, while a system that is countable is said to be stable. Okay, great. And we're saying that this is for all n. If for some bounded input sequence xn, the output is unbounded, then the system is classified as unstable. So a bounded input should produce a bounded output if the system is said to be stable. Right? The interconnection of discrete time systems. We're just going to look at this briefly, and we'll call it a class for the day. So discrete time systems can be interconnected to form larger systems. So there are two basic ways in which systems can be interconnected. It can either be in series, which we call cascade, or in parallel. It can either be in series or in parallel. And these interconnections are illustrated here. So we have one system T1 and another system characterized by T2 in series. You have an input and you have an output. Okay. On the other hand, you have two systems characterized by transformations T1 and T2. Okay. And you have one input Xn and one output Yn. Okay. So in the cascade interconnection, the output of the first system, okay, is that the output of this first system is T1 Xn, meaning that our Y1 will be T1 X1. Okay, Y1 is a product of T1, but of course Y2 will be a product of both T1 and T2. So the output of the second system is now T1 of Y1, which would be T2 of T1 Xn. We observe that systems T1 and T2 can be combined or consolidated into a single overall system, so that TC will be T2, T1. Consequently, we can express the output of the combined system as Yn equal to TC, where TC is T2 times T1. In general, the order in which the operation T1, T2 are performed is important, since T2, T1 is different from T1, T2. Okay? So for arbitrary system, if the system is T1 and T2 are linear and time invariant, then TC is a time invariant system, and T2, T1 is equal to T1, T2. The order in which the system processes the signal is not important. Okay, since T2, T1 and T1, T2 yield identical output sequences. And the proof of A here follows from here. You can actually look at how it is proved, to prove that time invariance would lead to the order of implementation not changing. Okay, so systems can be interconnected. When they are connected, when the interconnection is in series, then the resulting when the interconnection is in series, the resulting process is uh, the resulting process is given the resulting process is given as a multiplication, whereas when they are connected in series, the resulting process is a sum. Okay, y3 from here is the sum of y1 and y2, so that y3 is y1 plus y2, first which gives the operations t1 and t2 as a sum. So you have t1 and t2 to give you TP. And we're saying that in general, we can use parallel and cascade interconnection of systems to construct larger, more complex systems. Conversely, we can take a larger system and break it down into smaller subsystems for purposes of analysis and implementation. And we shall see this later when we design filters. Interconnection of systems will become very important then. When we meet next time, we will look at analysis of discrete time invariant systems. Okay, when we say that there is an operation, how do you analyze the operation? When you say there is a multiplication, how do you analyze the multiplication? Okay, for today, that's going to be how much work we have done. Okay, when we meet again next Friday, we'll do analysis of discrete time invariant systems, and more importantly, we will do the convolution, how to multiply two systems together. Thank you.